We've been discussing evaluating work integrals, and now here are a pair of examples of work being done by objects moving in 2D. So in this case, we've got a diagram that we call a vector field diagram. We're looking down from above on the XY plane, and at each position in space, we've got a vector with a magnitude and a direction. An example of this sort of thing that you're already familiar with would be a weather map showing wind, mapping the direction and speed of the wind at every point on a map that you're looking at. Another thing to imagine might be, say, since it's called a vector field, like a field of grass. So there's a blade of tall grass at every point on the field, and when the wind is blowing, you can tell at each point the direction the wind is blowing by the direction the grass is pointing. And you can also tell how strong the wind is blowing by how far bent over your tall blade of grass is. So this vector field is sort of a way of visualizing a quantity, some vector, like say wind velocity, that has a different magnitude and direction at every point in space. All right, well, in this example, it's not wind that we're looking at here, but say water current. It works just as well. If we're looking at the surface of water here that is flowing, we can see the direction and magnitude of the rate of water flow at all these different locations. So a jet ski moving near a buoy in the ocean, here's our buoy at the origin, is moving with initial velocity v0 to the south. Okay, north is straight up. When it loses power at t equals 0, time 0, and begins to be carried off by the current. So using the buoy as origin, the current exerts a force on the jet ski according to this function. Okay, now here we have a force as a function of position of both x and y. The idea being that the moving current here would exert a force on your jet ski depending on where the jet ski is. So we can see that over here on the east side, the force exerted by the moving water is stronger than over here on the west side. And we also see that that force is changing in direction. So this vector field that we're visualizing is actually a graph of this function right here. Note that the x component of the force, Fx right here, is a function of position x, so that the larger the x value is, the greater the x component of the force. On the diagram, we see the further we go in the x direction, the bigger the x component of your force is. X component of force, x component, x component, x component, x component. You can see the x component getting bigger as x gets bigger. A is a constant and B is a constant. Whereas the y component of the force is just B, a constant. So your y component is the same at all locations in this region. So the y component is constant, but the x component depends on position. So there we go. We have a force with both x and y components, and the components themselves are functions of position. That produces this vector field map. Okay, we want to find the work done on the jet ski by the force of the current, the force that's depicted here, as the jet ski moves from this initial position to this final position. Okay, let's sketch in those initial and final positions. Let's see, 2 meters and 4 meters. Let's say that is about here. We'll call that R1, the initial position. And our final position to 12.5, so 12.5, let's say about there, will be R2. Okay, so it moves from here to there, and we know its initial velocity is to the south. Initial velocity to the south. We don't know the exact shape of the path, but I think we can kind of guess. Let's see, if its initial velocity is to the south, so it starts out moving due south, and given this current, we can see that the jet ski will sort of slow down at first, being opposed by the current, and gradually be pushed off to the east over here over time. So let's say maybe something starting out due south and then gradually being pushed off like that. Okay, so some curve roughly like that would be the trajectory of our jet ski being pushed by this vector field. Okay, we want to find the work done on the jet ski by the force of the current. Now note that we don't know the exact shape of this path, but we're not going to need to know the exact shape. We just need to know the starting point and the ending point and the force function, and that will be enough to solve our integral. Let's set up the integral. The work done by that force will be the integral of f dot dr along that black path that I drew, along that curved path. Okay, we can break up that interval and break up the integral into an x integral and a y integral, the sum of the two. So the integral of fx dx from our initial x position, 2 meters, to our final x position, 12 meters. Here we're assuming that we only moved in the positive x direction, that there were no turnarounds, no doubling back. We only moved in the x direction. That allows us to put in our limits easily like that. Plus the integral in the y direction, fy dy, going from our initial y coordinate, which is 4, to our final y coordinate, which is 5. 4 and 5. Okay. Now we can plug in our integrands here for fx and fy. So this becomes equal to the integral as x goes from 2 to 12 of fx, which is ax, then times dx, plus the integral as y goes from 4 to 5 of fy, which is just b, some constant, dy. All right, find our antiderivatives. Antiderivative of ax with respect to x is 1/2 ax squared. We're going to evaluate that as x goes from 2 meters to 12 meters. Plus antiderivative of b, a constant with respect to y, will just be by. As y goes from 4 meters to 5 meters. Okay, and we've got numerical values here. You can plug in those values yourself and confirm my arithmetic that this expression will come out to be 2100 Newton meters, and this expression will come out to be 20 Newton meters for a total of 2120 Newton meters of work done on our jet ski by this force, as we move along that path there. Okay, so there we had a two-dimensional, a work integral done for an object moving in 2 dimensions. So we needed both of these terms here that came from this definition of work, which we can break up into the sum of integrals in the x, y, and z directions separately. We had no z component this time, so we just had these 2 integrals to perform. Okay, before we move on from this example, I want to note that in setting the upper and lower limits here, I said some words earlier about not worrying about reversing direction in the x direction. But if you look at the y direction, you can see we clearly did. We went in the negative y direction, then we went back in the positive y direction. We did have a reversal in this case. So is that a problem? Was I too hasty in just setting up my limits like this when we have a complex path that involves a reversal? The answer in this case happens to be that what we did was correct. We did not need to worry about that reversal because of the nature of the force that we were given. We were given a force that was a function of position, a very special kind of force that falls into a category that we call conservative forces. This happens to be a conservative force because it is specifically a function of positions. That's a topic to discuss another time. But for now, the point is that when you have a conservative force, you can easily set the limits knowing just your starting point and your ending point. You don't need to know anything about the path in between, and you don't even need to worry about any reversals in between. Conservative forces are very nice to work with in that way. Okay, so more on that topic another time. Now, second example. A roller coaster. So we're looking at a roller coaster track from the side. So this is the vertical direction, and here's our track. Here's the first hill, and we're going to go down that hill, up this hill, through that loop-the-loop, then over this last hill, and here will be the end. So a roller coaster car rolls freely from the top of the first hill to the end of the ride. A total length of track of 1.2 kilometers. So the total curved length of the track here is that value. So if you straighten this whole track out, the whole length of it would be 1.2 kilometers. Along the way, the car is subject to a force of friction that is going to vary in magnitude and direction, but is always parallel to the track and has an average magnitude given by this value here, 100 newtons. Find the work done on the car by friction from the top of the first hill to the end of the ride. So you want the work done on the car by friction, the effective friction trying to slow the car down as it travels through the whole roller coaster. Let's set up this integral. The work done will be the integral of our force of friction dotted with dr along that curved path. Okay, let's consider a few different points along that path and try and visualize that force of friction. Let's say here, the top of this hill, over at that corner there, over at that moment. At each of these points I want to draw in our infinitesimal instantaneous displacement vector. So a little dr, a tiny step forward tangent to the path pointing in the direction we're moving at that moment. Little drs. And then next, draw in that force of friction at all of those moments, which we're told is always parallel to the track. And we know friction will be opposing the direction of motion. So if it's a kinetic friction-like force or a drag friction-like force, it'll be opposite your velocity at each moment. So the velocity being parallel to our displacement, our friction will be tangent to the path, but anti-parallel to displacement. Okay, we're told that it varies in magnitude, so I can show it having different magnitudes at different times. That's okay. And we see clearly it varies in direction, pointing in all those different directions. So all those red arrows are our forces of friction. So we know its direction is opposing the displacement, and we know its average value is 100 newtons right there. Average magnitude is given. All right, so how can we evaluate the integral in this case? This time, instead of using this expression for our work integral, instead of using this definition, this way of expressing our dot product, I want to use this way of expressing our dot product as the magnitude times the cosine of the angle between those two vectors. So I can express this dot product here as the integral along the path of the magnitude of the force of friction times the magnitude of each displacement vector. That would be a little distance there, your tiny distance forward that you're moving, times the cosine of the angle between those two vectors. And note that since they are anti-parallel at all times, the angle between them is always 180 degrees. That's really the key. And cos 180 is -1. And so, since we know the average magnitude of the force of friction, we can pull out that constant average magnitude from our integral, pull out the -1 as well, and we're left with the integral along the path, the sum of the magnitudes of all the displacement vectors. Okay, this is a subtle point here that we need to discuss a bit. What do I mean exactly? We're summing up an infinite number of infinitely small things, that's an integral, but we're not summing up all the displacement vectors, the little dr's, we're summing up the magnitudes of all the displacement vectors. Let me try and suggest what the difference is. Here I have some path starting here and ending there, and I've drawn along that path a whole bunch of little displacement vectors, dr's, all sort of lined up one after another, all pointing tangent to the path, locally tangent to the path, and the sum of all those little displacement vectors, the integral of all the little dr's, the sum of them is going to give us the delta r from the beginning to the end. The delta r, the vector pointing from the very beginning of this chain to the very end of the chain. We've lined up these vectors to add them in head-to-tail method. So the sum of all of them, the infinite sum of this infinite number of infinitely small displacement vectors, is a vector pointing from the beginning of the chain to the end of the chain. So that would be the sum of all the displacement vectors. But that's not what we're doing here. Here we're summing up their magnitudes, which came from magnitude here from our definition of dot product. Dot product of these two vectors gives us the product of their magnitudes times the cosine of the angle. We've taken care of the cosine of the angle with that -1. Now we're just adding up the magnitudes, the actual lengths of each of these. We're adding up all of those lengths. So what we're doing in adding up all the lengths, if instead we are summing the lengths of all those vectors, what we're doing is getting the total length of the path. So if we stretched out that path into a straight line, the length of that green line would be the result of summing the magnitudes of the displacements. So this would be our total path length. That is the total length of this track here. So I'm arguing that we can evaluate this work integral by taking the opposite of the average magnitude of our force of friction, 100 newtons, then times the total length of our path, 1.2 kilometers, to get negative 120,000 Newton meters. So key idea here was that this represented the sum of all those little distances, sum of all those steps, giving us the total path length. So this is great. Even though we didn't know the exact shape of this path, I just drew a curve at random. Even though we didn't know the exact shape, knowing the average magnitude of the force and knowing it's always anti-parallel to the displacement allows us to still compute the total work that was done. Of course, that work comes out to be negative, since that force of friction was opposing our displacement at all times. That force of friction did negative work along this path.